So Bjarne introduced kind of a discontinuity to introduce a nonlinear objective function instead of the linear problem by having the choke go to 0 if the value is less than 15 or whatever, 0.15. Instead, we're going to look at a different kind of nonlinearity in the same problem. And what we see here is the sheet that you have, the Excel sheet that you have from Mike's handout CD, which is called 60-well coning problem. Okay, so you have the base problem that we're going to look at here. But I've added to this some plots. That's basically all. And Mike calls this the experiment, the laboratory, the laboratory, the nonlinear optimizer laboratory. So it's kind of a way that you can study different optimizer solver algorithms for linear and nonlinear problems. It's an approximation of 60 wells instead of 5. 60 wells is, let's say, a more realistic magnitude problem for a complicated field along the lines of Urku, which is Nizana we're working on the last couple of years. And Troll is, I guess you could multiply by a factor of 2 or 3 to get the total number of wells they're trying to control in the Troll field. How many wells are there?
100 of both.
Yeah, so double the size. But you can easily double this to 112 or 120 if you like. And with this spreadsheet, I just want to go through it a little bit, how you can make use of it if you're interested in this problem. Because I'm interested, Mike's interested, Nizana's interested because it's related to her PhD research. And altogether, it's a very interesting problem. And I don't think it's really been looked at. So I thought I'd just make a few comments about it. It gives you a laboratory, as Mike calls it, to do study of different optimizer solutions for a relevant problem. The problem is that we have today 60 wells, which we have a description of their today's performance, meaning that we have a choke, we have a gas, oil, and water rate today. So we kind of know today's choke deliverability, if you will, what the well's delivering for a set choke. And then what we're going to do is we're going to introduce how the gas rate and the oil rate and the water rate will change as you change the choke. The one model that we've been using the first 2 days of the seminar is just a linear dependence. You increase the choke by a factor of 2, you double the rate for all 3 phases. And now what we're going to do is we're going to introduce a little more general relationship between rate and choke that gives a nonlinear behavior. So in this spreadsheet, instead of giving only the maximum oil rate, which is what was given in Mike's sheets, and assuming that the gas-oil ratio and water cut are constant, independent of the choke size. Okay? That was the assumption in the original model. We're giving, in a sense, a maximum gas, a maximum oil, and a maximum water rate. And in addition to that, so we're doing that. And in addition to that, we're giving the exponent to which it the rate changes with the choke. So this is a little more general treatment. So this is the way this spreadsheet works. So these are given. The maximums are given as numbers, and then you can select the NG, NO, and NW as input. So for example, you might if all of these are equal, then you get some properties. For example, if they're equal, then the gas-oil ratio is a constant as a function of drawdown, similar to the assumption we had earlier. But you could choose Ng equal to 2 and NO equal to 2. The gas-oil ratio would still be constant, independent of choke size, but the curves themselves of rate versus choke would be nonlinear. Do you see? If the water exponent is also the same value as the gas and the oil, or if oil and water are equal, so if we just write Ng equals to NO, we say if, then that leads to gas-oil ratio constant. And if NO is equal to NW, that leads to the water constant, or water cut being constant. Okay. You can see these relationships down here. They get kind of complicated, so it's not intuitive. But at least for these simple cases, we can get more or less the same performance, constant GOR and constant water cut, but with a nonlinear dependency of rate on choke. Okay? Now, if all of these are equal to 1, then we have a linear problem. And we should use a linear solver. And if we do that, it'll go through this procedure that Bjarne talked about, which is this linear programming and simplex method, whatever it's using, and you're guaranteed a solution that will meet all the constraints and maximize the net present value, or in this case, the oil rate total. And so that's the simplest problem. So the way this spreadsheet works is that here are the 3 exponents that you can set. And then you've got this minimum choke. I think we were using 0.15 mic and 1, maximum choke of 1, whatever you can set. And those limits are the same for all wells. It doesn't allow, you could change that, but it doesn't allow you to change the limits for a given well. Okay. Now, so everything in red is input. These gas, oil, and water rates for each well, maximum, are coming from somewhere. Okay? And because I want this to be a laboratory, I've created a kind of a way to create a random set of these maximum gas, oil, water rates. So you can test your algorithm, you can test various problems. For a set of 60 wells, maybe representing Troll in one case and Uruku in another case, and your field, you can have all sorts of variation of these 60 wells, strong contrasting gas-oil ratio, water cuts, and so forth. So to create, you can just manually go in and change these, or you can go to this well QOM sheet. And the way this works is that every time you hit F9, it's supposed to recalculate. It's not doing it. So, random number F9 to update. Data. Tools, options, calculation, automatic. Did it change? Maybe the keyboard here is not working. Yeah? Not the F9 key. Okay, well, on your computer it should work. We can do it manually. Tools, options, calculation method, and then if I say calculate now, you can see 1260 will change to 1143. And it does the same for, it does the oil rate that way, and then it assigns a gas-oil ratio randomly between 500 and 3,000. Okay?
Maybe just worth to say that this function run, with parentheses, give you a random number between 0 and 1,
Yeah.
and up to 100 numbers in a row. Okay,
Is it limited to that?
Yeah.
Okay.
100 numbers, it will give you between 0 and 1.
Okay. So anyway, this is going to be a number between 0 and 1 random. So the GOR range is between 500 and 3,000. And the water cut range is between 0 and 0.4.
By the way, Kurt, is that kind of an oil field, or is that a metric in the term of the range? You have something for all the magnitude in the mine? Or?
I don't know. I've written MCF per day. These are, I don't think it really matters.
Look at the GOR.
GOR is from 500. It looks like cubic feet per barrel, but it could be.
It's an oil field.
Yeah. Yeah. So, okay. So if you change this to 100 and this to 600, then you would get something more like cubic meters per cubic meter. So. But anyway, this is a way to generate a set of wells with different characteristics, and then it's translated into these maximums through kind of through the equation here, and then you can just copy these. For example, to do a new laboratory experiment, you just copy these into here with a paste special values, and now we get a whole different problem. A whole different field, and okay, and these give you the maximum GOR and the maximum water cut here for that particular well. So at the maximum rate, which would be choke of 1. Now, the blue numbers are the 60 variables that it's solving for. So what it's doing, it's solving for the 60 choke settings here that will maximize the total oil rate. Okay, that's the same as your problem. And so the total oil rate is just calculated by, there are 60 wells, and each well is assigned a separator like you did in your exercise. And here there are I believe six separators. Now you could change that set of assignments if you like, but basically they're equally distributed, 10 wells per separator. Okay? But those could be changed. And then it adds up for each separator the oil rates here, and you can see that sums to 72,767 right now. That number is brought over here. Okay? And that is the target of optimization. That's to maximize that. So if we go into the solver, it should be pointing to that number there. That's going to be maximized. And then it's changing the cells, basically all of these choke settings from 16 to 75 cells. So 16 variables. And all of the constraints are set here with respect to the choke being greater than 0.15 and less than 1. Okay. And then the other constraints, right. The other constraints is that you have 6 constraints on the gas separators, the 6 different production separators. Right now we're violating the constraint here. Of course, we haven't run the optimization yet. So let's just run the optimization and see whether we satisfy all of these constraints. It's working down here, iteration 42, 46. A little more effort being made than previously.
You're still linear, right?
Okay. Well, But you see, it meets all of the gas constraints. In fact, it drives it to the limit. The problem we're solving is using a nonlinear model. I haven't selected the linear model. But if you look at the exponents here, they're all 1, so it is a linear problem. So we're using a nonlinear method to solve a linear problem. Okay, so it met all of the constraints here, and likewise on the water, it met all of the water constraints. So it's pushing the production separators to the limit, maximizing the oil production. And this is the set of chokes that it found here. So what we can do is that we can, if we want to compare that, we can copy that set of results here. I have a column for if I want to make a comparison. So I copy it over here, paste special, and values. And then I want to copy these because these are the cases that this is the set of exponents and the range here. And then this we need to copy as well. Like that. And I've got another one here. I'm just going to delete that. That's from something old, some old experiment. So now, for example, if I want to, that was a problem that started with some arbitrary set of chokes that I had picked. I don't know where I got them, right? It started from a set of arbitrary chokes. So now, based on our experience yesterday and today, we know that you better be careful. There could be multiple solutions. So we want to go looking for other solutions. Now I got 60 wells, and I can go in and type, I'm going to use 0.5, or I want to use 0.4, a constant value. But instead, I have a way here of generating a random number between the minimum and maximum here to get us started. Okay, so we just copy that over as the starting point, paste special, and values. Okay, so now that's the set of starting points, and you can see that we're of course violating all these constraints on the gas and the water. So it's not a feasible solution for sure. It's not certainly not the maximum, and we've got a lot more oil being produced, but violating constraints. So now we can now because it's a linear problem. Okay, if we use the linear solver, Bjarne says that it's guaranteed to give us the right solution. But let's not go there yet. Let's just try to solve it with the nonlinear method, but with a different set of initial values. Okay, so we'll solve. Again, it'll work. Now, an interesting thing about Excel Solver is that when it's using a nonlinear method, apparently it has so much smartness that it's able to take analytical derivatives of all of the objective function with respect to all the variables and constraints. Because if the formulas are in the sheet, it does some kind of calculation of these derivatives. I think. I'm not sure, but okay. So let's look and see the result. Okay. So what we see is that it looks like it came up with the same solution the second time from a different starting point. Our comfort level is increasing that this nonlinear solution is giving us the right answer, independent of the, you see how it's the same thing here and here, and it's the same thing here and here. Now how can we check to see whether this is the solution? Well, we go in and we select the linear model. And supposedly, from what Bjarne said, it's guaranteed to give us the solution. Right? That's what he says, so we'll believe him. Okay. We'll close it down, and let's start with a different set of choke values. Let's just start with 0.1. That's outside. It's not even in the feasible range. Okay? So now we've got a very low rate, which you would expect. But we're outside the feasible range. It has to be 0.15. And we'll run the linear solution from here with a bad set of initial estimates, linear model, and solve. My goodness, that was fast.
No iteration, how do you do it?
I didn't see anything happen. You want to try it again? Huh? You don't believe me. Okay. Restore initial values. Okay. Now you guys got to be awake here. Tools, solver.
Try to do it with stepwise iteration. You'll see.
Okay. Options. Show iterations. Went too fast for Mike. He has to have us.
Too quick.
Okay. Solve. Okay. 1. Solver pause. 1. And you can watch the choke sizes as they're changing. 2. Don't look at these here, because these are random. So don't. Okay. So we can't see anything. Yeah. Here you see it one changing. Continue. Continue. I don't know if you notice it, but if you look down here at the cell, it looks to me like every iteration so far, the oil production has increased. So it's got some kind of smarts that it keeps every new guess. It doesn't seem to be going like this. It seems to, I don't know, maybe that's a part of the linear program.
I don't think it will have much less iteration. They're just going much quicker.
Well, but you have to realize in the nonlinear, it has to calculate the derivatives. Okay, maybe they're not analytic. Maybe so. There's a lot more calculations behind the scenes.
Because I think you'll end up with the same amount of iteration. But
I don't know. Okay, so it took, I don't know how many. Okay. A Newton method, yes. Yeah. This is linear, what we just ran. Right. Yeah. Okay. So basically, we can feel now we've got a comfort level that this is right. Okay. So now let's do the following. Let's change to just not quite linear. Okay. And let's start with again 0.1. Okay. And now if we try to use the same solver, which is the linear solver, the conditions for assumed linear model are not satisfied. It is smart enough to know that you've got a nonlinearity, even though it's small. So we can't use the linear solver. We go in and change that, turn that off, and solve. Oh, we want to stop that because we want to turn off the step-by-step, or else we'll be here all day. Might be here all day anyway. Okay, solve. Okay, so now it's off, working away. Okay. Okay. So now what you see is that the choke sizes are radically different, right, than for essentially the same problem. Okay, I'm going to copy these over here. Paste special. Okay, let's just try to run it again from here. Maybe it's stuck. Maybe it's found. Let's just try it. Solver. Okay. Didn't change much. Okay, so it's at some kind of minimum, but it's probably not the global minimum. I don't think.
We had a higher total void rating with the previous choke.
We had a higher. So it did change it a little bit.
No, not from this to that. But if you use choke setting from the linear model, then you end up with 84 something.
Yeah, you should essentially end up with the same answer. So let's try that. Let's just take the choke settings from the linear model problem. That's kind of cheating. Okay.
Well, that's not. You wrote over those. So.
Oh, I wrote over those?
Yeah. Basically.
Okay. All right. So let's go back to 1. Let's go fetch them. All right. Tools, solver, options, linear, and solve. Okay. So then we go save those. Okay. And those are the, yeah, so that's okay. Now, we'll change these to 1.01, 1.01, and 1.01. Oops. 1.01. And now we can't run the solver with linear because it's no longer linear. We already know that. So we'll start, though, now from the initial, from the final converged linear problem, and we'll start with those initial values and see whether it ventures off somewhere else or if it stays tight, close to this solution. Okay, 5 iterations says I'm done. And you can see the kind of small changes you would expect. Okay, so let's try to solve it one more time just to make sure it's there. Okay, so it's definitely found a minimum, or in this case a maximum. Okay, so what you see is that it's clearly dependent on the initial values, even though it's a near linear problem. So we have a real problem. We have a real problem because in reality the actual behavior of these could be radically different than linear, certainly. Okay? Let's just try something like second, second, second. Now, what I've plotted in the next figure is showing versus choke how the maximum, the rate over the maximum, this is kind of like an IPR curve, looks like. So all of the phases look the same. They have this kind of curvature. But the GOR here and the water cut here are constant. Okay? Because the exponents are the same. But it's a nonlinear problem. Okay, we're violating, I suspect we're violating some constraints. No, but we're not meeting the constraints, so we should be able to produce more oil. Currently it's producing this much oil. So if we run this optimization, working hard. Okay, solver found the solution, all constraints. It took some it looks like all the constraints. But let's just run it one more time just to make sure. Okay, just you never know. Okay. So it's found the gas oil ratio, water cut's the same. let's just look at the choke differences here. It's actually quite similar. This one's different. The rest of them are quite similar.
Please, can you just go back to the
Let's just look through here.
whether you make the statement that they are the same if the exponent is the same? You develop the analytical.
So these are the same. It doesn't matter. Okay, so they're quite similar, and then there starting to be some differences here.
If we got more oil.
And we got more oil.
So why?
Okay. Good.
That's not
Okay.
good.
Now, the problem with this solution here is what? What's one of the problems with this solution? We have no way to find out whether it's a global solution. We can't go back and say, oh, let's run the linear optimization and verify, like we did last time. There's no way other than doing what? Trying a new, okay? And that's why you have this random number generator here. Or you can do it, with constant values, whatever you like. Base value. Okay. Of course, we have to save these that we got. Actually, we can save.
That's not guessing, that's the random. You've already
Oh, is that it? Oh, okay. Copy. Yeah, I've got to have these.
Shift Control V, then you mark the whole column.
Okay, so now we'll start with a new set of values. We've got less oil, but we're probably we're not meeting the constraints. Try again. Solve it. Now the last time when we did these, we started with I think the linear problem guess, right?
Even change the folder, the problem is not.
No. The nonlinear, when you go to the nonlinear solver, you kind of lose the ability to know that you found a global maximum. So you have to do something to start looking around, okay? And one way to do that is to start with different initial cases. And if you always come to the same solution, you can feel comfort. If you keep coming up with a new solution, then you don't know. Okay, so it's still working 200 iterations. Okay. And did it get the same result? Yes. But it took twice as many iterations. Okay, so we like that. We do it 2 or 3 more times with different random initial estimates, and we feel like we found a global minimum, a global maximum. Okay. So this sheet and this, in a sense, this laboratory, if you will, gives you a more real-life problem of interest, for sure interest, that can let you study different solution methods, different, and it's a very interesting. And then if you change these, you can also get the behavior of gas-oil ratio being different than constant. For example, if we change this to the gas being, I don't remember exactly 1 and the water being 5. let's see, that gives the GOR decreasing. We don't want that. So we want 2, 1. Okay, so here we get both water cut and gas-oil ratio increasing. That's what everybody thinks happens. I don't think so. Everybody else does. So now we've got a strong GOR relationship increasing, water cut increasing as a function of the drawdown. And this plot is not in your sheet. You have to create this yourself. Okay, but it's a way to anyway. I'm not going to talk any more about it, but it's I think it's a it has a lot of interesting characteristics to it for studying optimization, solvers, initial, and so forth. It's
it also gives you enormous incentive to understand what happened when you change the choke, what happened in terms of pressure in the pipe and in the choke, and what happened in terms of inflow into the well. Gives you a very strong incentive for that.
okay, so that's I think that's it. I just wanted to introduce this. It's a sheet that you can use yourself or not, but it's any questions about it? It's okay. All right. So at this point, we'll pass it over to. I think Alex will, in this first initial SB3 problem that you're going to show, I can talk around it, and then so. Okay. Now, okay. Everybody stand on their head. Okay. I won't make you do that.
Why they turn the menu upside down?
Let's do. Okay. Check your geometric coordination, I guess. Okay. Now, because what's being shown here is not shown on my screen. We could do a Webex and get it recorded. Actually, why don't we do that? Because that's better than this. What's being recorded here? Do you mind setting it up? Okay. So what we'll do is that my screen will show what is on his screen will be recorded, and then everything will be okay. Are you sending through Skype when you get that? Okay. Your meeting information was not valid. Please try again.
Did you not? Did the link not work?
Huh?
Didn't the link work?
For some reason, I could have done something wrong.
I'll try to send it to you.
Yeah, try one more time. some reason it's starting up Windows Explorer instead of Firefox, and it doesn't seem to like. I'll try it in. Your meeting information was not valid. Please try again.
If you try to go to meetmenow.webex.com.
Meet me now. meetmenow.webex.com.
Then you punch in meeting number. That's the number, the last number in the link message.
Okay, for some reason it's not. www.meetmenow, one word, .webex.com.
Yeah.
Huh. www. Meet.
No www.
Oh, just meet me.
Meetmenow.webex.com.
I thought everything was www. Even the country songs have www in them. I mean, it's like, okay, and then which one?
Then you just push in the meeting number. It's 941-894-6.
Attend meeting.
Yeah.
And then, what is it, 9?
941. 941.
Yeah.
894.
Yep.
654.
Okay. A little bit of setup, but okay. Actually, if you give me control, then I can just go through this and okay, this is a
Minimize the meeting.
can you do that?
You have to do it. I don't have control of the computer.
But I don't see it on my.
Okay. Don't move your mouse.
Okay. Now I can take over? Okay. Okay. This, what we're going to talk about the rest of the day, just, the hour that's left, is a means by which one can integrate models and do optimization outside of Excel.
You export the sounds now? Or?
Yeah, I think so. I think maybe. Is this yours? Okay, just a second. I don't know if I am or not. We can see. Yeah, I think it's on. Okay. Okay, now. Okay. So the idea is that we've spent the last 3-4 days doing something in Excel, which is building an integrated project with various models representing reservoir, production, process, economics. Okay, that's what we've done. That's the purpose, that's really the whole intention of this integrated operations program, at least the part that we're working on. And this seminar is supposed to give some insight into what are the requirements, what are the advantages of doing integration and optimization. But we did it within Excel with a very simple reservoir production model, simple process, and simple economics. So now the question is there hope for there being more complex model descriptions of a petroleum operation where we don't use just Excel to build the models? That we take, instead of our simple little back pressure equation, that we have a reservoir simulator representing the well behavior. Okay? It might be a reservoir simulator describing a single well or a couple of wells or the entire field, representing the reservoir production, maybe the vertical flow performance of 100 wells or 2 wells. Those are the kind of models we work with today on a regular basis. The problem is that they take 3 hours and 30 hours and so forth to run. But what we'd like to do is to be able to take our simplified Excel solution, for example, and verify it with a rigorous reservoir simulator, HYSYS process, economics package, and verify that our first order effects have been modeled correctly, that we're getting an optimal development strategy that is consistent with these more complicated models. Now, the one way to do that would be to send back to the reservoir group, okay, the results from our little Excel spreadsheet and say we need 42 wells producing for 8 years with these rates. Please run that case on the more complicated model. And then they could say, well, our results are quite similar to yours, so that's good enough. But instead, what we're going to look at is a software environment that functions like Excel, if you will, where each cell in Excel can be containing a data or an equation. An equation is a model, right? That's the way we used it. We set up an equation to solve for the rate. That was our rate model. We did the calculation of the processing with equations. Those were our models. Some of the cells contain simply data that were used by the models. So in order to replicate the same mechanism of launching models that are accessing data, integrating the data from results from one model, input, output of one model, input to the next model, we have to have some of the same functionalities in any solution that will allow us to do the same integration and optimization. So we're going to look at a software that we've been working on and developing to provide that kind of capability, okay, outside of Excel, but using the applications that are currently used to describe reservoir, production, process, and so forth. And several people in the group, Shinazan is doing it on a commercial basis, Stainer and his PhD research, as well as Alex. And so we're using this application. Maybe Michael's going to be able to use it to look at well startups at Statoil Hydro. It's a mechanism that allows you to launch various applications, integrate them together, and have an optimization on top of that to control the cause and effect of data, model, data. So how do we do the same kind of thing in Excel that is so easy? Punching in an equation, okay, linking to a cell number. So we're going to show you just a couple of simple examples that illustrate that. In fact, I'm going to let you take control instead of me doing it, and then I'll just kind of talk through. How do I give you back?
Just don't touch your mouse.
Okay. It's like when kids want candy. Say just don't touch and steal it. Okay, then you can have some candy. So, all right. Okay, so this is an application called Pipet, and it allows you to launch any other application that you have on your computer. Okay, so if you can launch Eclipse 100 as your simulator, you can launch it from within Pipet. Okay, and then what this does, as you'll see here, we've built 3 little boxes. These are not just cosmetic boxes that tell you something, but we built this project into 3 parts: a reservoir simulation part, a surface processing part to get products, and taking the products and converting to value, economic. Very similar to what we did in Excel, right? These 3 boxes represent what we call composites. Okay, inside each box there are real things. Okay, so if you click on, now the problem we're looking at here, is a compositional reservoir simulation. Well, it's a gas condensate reservoir. Okay, so we're looking at a gas condensate reservoir, which in our Excel project we had a dry gas reservoir, so we have more complication. We're going to model the reservoir with a compositional 3-dimensional reservoir simulator. We're going to look at gas injection and how gas injection can improve overall condensate recovery and economic value. Okay, and so inside the reservoir part, to do the reservoir simulation, what do you need? You need a data file, an Eclipse file. In this case, it's called Sensor, the reservoir simulator. You need an input data file. And in this software, files on your computer are represented by these blue triangles. If you want it to be another color, you can change it. But by default, that's what it looks like. And when you see one of those, it's actually linked to a file. So if you double-click on it, it'll open that file up, and you can edit it or do whatever you want with it. And that's an input data file to the reservoir simulator. So if you go out again, the next object is an oval, and that represents a process or an application that you're launching. It can be an Excel spreadsheet, it can be Eclipse Reservoir Simulator, HiSys, anything that you launch on your computer, you can just put it on there and say launch it. Now, why do we have them connected? The reason we have them connected is because when you launch Sensor, it needs to know the file name, and it'll fill that in for you without getting into the details. You'll have an association that it knows, the Sensor application knows that that's the input file. That's the one reason. The second reason is that the order in which you run these simulations, and in the problem Alex will show you later, you'll see that we have 2 reservoir simulators being launched in parallel. So it needs to figure out which one to launch first, or does it matter? If it doesn't matter, then it needs to be able to just launch them in parallel. If there's a sequential order to what things are launched first, for example, if we go up a step, you need to run the simulator before you do the process calculations. You need to do the process calculations before you do the economic calculations. So these connector lines are telling Pipet the order dependency of the different programs that you're launching. And in the background, it'll orchestrate the launching of all these applications without you having to think about it. But it means that you have to tell it what are the files connected to the processes or applications, like we do here in the reservoir. The input file, the application, and then what it does is it sends out output files. Now this reservoir simulator, Eclipse, generates RSM files, print files, a number of files. Okay? If you want to use any of those output files, then you need to drag them onto our canvas. This is called a canvas. Okay? Because those files might be used by other processes. That's the case here. If you go inside, now we have a composite, and as I told you, a composite is nothing more than it's like the old TV program, you know, what's behind the door? You know, and they open the door and there's a new car, you know. Yeah. So when you see a composite, you always know there's something underneath it. Now there might be just another composite or two. You just have to keep digging until you see whether you get the car or you get the ugly, guide to take home. Okay, so here we've got a couple of files. The output file, that's like the PRT file in Eclipse. This PSM file is like the RSM binary file with all the results. The binary file is then taken by an application that extracts output, which is the molar. It's a compositional simulator. At each connection in the producer and injector wells, it extracts the compositional stream for each time step, makes that available to an application called Streams, which is a Pipette application. And you can then do things with the compositional streams from each well and each connection. And basically you end up getting the total well molar rates in a file. And that's taken, that information is then, so you get all these CO2, nitrogen, for each time step. You get all this information. These are molar rates. And then you can do stuff with that. Okay? Well, what are we going to do with that? Well, we're going to take that file information up a level through that socket. And then we're going to go up another level. And we're going to send that to the process group, because the process group wants compositional streams. And what does the process do with it? Puts it through a separator, dew point controller, whatever you like. And it creates products. So these various files are going to contain file information because it goes through HiSys or whatever program you're using for the processing. And it creates these 4 files with the 4 products, each time step. Then those products should be sent off through these little connectors, to the economics program. And in the economics program, you have to convert the volumes or the masses to value, to dollars. That's done through another set of processes. And then finally, you add everything together. And when you add everything together, you also do discounting in the economic model with the discount factor. So just as an example, okay, we're going to do discounting. But where's our discount factor? Where's that 10% number? How do I link into that number? I want to change it to 0% like Michael did, or I don't remember who took this number and changed it from 10 to 0%. How do we do that in this environment? So Alex will show you. See, that little box there is actually a file containing the number 10 somewhere. You go in to edit it. It's kind of hidden, but it's in there somewhere. See the number set DCF 10. So that's the syntax in the economics program. So if I want to change 10 to something else, then there's a mechanism for doing that. I don't know if we want to go through it, but it's a mechanism.
Is that the program that you wrote yourself, this economy, or is it a commercial program?
No, this is just a simple hand-grown, like doing it like in Excel. No, it's actually using the Streams program to do it. Yeah. So if we go out of here, there's a mechanism. I don't know that it's important to, maybe we illustrate just with one number, just to show. Yeah. So there's a mechanism called links. And what it does is it lets you go in to any file and lock on to any token, be it a number or text or anything. Okay? And if you go down to that, you can, it's already defined. Okay? And now because any text file can have, it can be hard to identify that particular number, you have many mechanisms for uniquely identifying that that's the number I want to fetch and change. So there's some logic that you can create, and you can test whether when reading that file we can uniquely find that number or not. Okay? So that's been done, and then that link becomes part of a library of links. You can create as many as you like, and those are like your number containing cells in Excel. So I don't know if are these, these are the list of the links that are in this particular project. The value, the type, the location in which file, and then there's a mechanism it has for linking onto it. So the same way in Excel that you're writing the equation, that's your model. And when you get to a link, you have to go link back to some number in another cell. This is the same mechanism for doing that. Okay, and then basically, when you run the project at the top level, if you launch this project, it'll first launch the Reservoir Simulator. It'll take the output from the Reservoir Simulator and massage it into a format that can be read and used by the Process Simulator. It'll run the Process Simulator, create new files with products. Those products will be sent to the economics program, converted to value, discounted, and we'll end up with a single file with net present value. Okay? So let's just run the project, I guess, and see what happens. Okay, yes. And by the way, because processes take a lot of time in real life, it automatically will sense, like when he ran the project, nothing needed to be redone because it knows that all the resources were updated. So the last time the Reservoir Simulator had been run, the input data file had a timestamp on it, and that hadn't changed, so it knew it didn't need to rerun the simulator. But we can modify that and say, kind of trick it into making it run. So now it'll runs the simulation, which, by the way, when this SB3 problem came out in around 1986, this took on a Cray machine, which was a supercomputer, for some of the competitors in that SB3 problem, took up to 10 hours, taking about 2 seconds now to run. Okay, it ran through the process, economics, and if you go to the end, you can, yeah, let's look at the NPV, that file. Okay, so you see the amount down there, $98 million? Okay, so that's the number. So that's like a cell in our Excel sheet. Okay? Now, if we go and change something in any of the data files upstream, like, for example, how much of the produced gas do we want to re-inject? Okay, there's a number in the data set, okay, which is a fraction of all the produced gas. What fraction should we re-inject? Okay, and that's a key variable. Should we re-inject, and if so, how much? So you go into that file, and there's a number down there. It's called ITARG. The number is 0.52. It's re-injecting 52% of what it produces as injection gas. Let's just change that to 0 manually. Okay. Rerun the whole project. Reruns the simulator, the processing, the economics, and we end up with a new net present value. Okay? So now we're doing the same mechanistic thing that we did in Excel. It's a little more complicated. You have to edit files and so forth and so on. And we get $90 million. Okay? So now, can we do optimization? And so I'll just let Alex kind of go through and show you how you do optimization. First, we define the different links. We're going to link to that number, 0.52. And then we're going to link to the net present value, 2 numbers.
It's already done.
Okay, it's already done. Yeah, so we can just go to the optimizer.
Yeah.
So there's a mechanism here. We can add one variable and one objective. So the objective will be the net present value, and the variable will be ITARG, which is this fraction of produced gas being reinjected. The limit from 0 to 1. And now we're going to link, because we've created this link to that number. We've got a whole list of links, and the one we want is that one there. Fraction injected. And then net present value, total net present value. Okay, so those are the two numbers. We define the one as an objective, the one as a variable. The one as a variable has a lower and upper limit. Okay? And you want to, and then basically if you change from 0 to 0.52, and you say run once, it'll run the project from here. And you'll see immediately it's running below, and you'll see the final result pulled in up above there. Okay? And now we can run an optimizer and say, well, what fraction of reinjection will give us the maximum net present value? And that you do by just pushing on the optimizer, and it'll run, and it'll just keep changing. You can watch the value of the 0.52, 0.42, 0.62. This is using a non-derivative optimizer method called what, Nelder-Mead? Nelder. Huh?
Nelder-Mead reflection simplex.
Reflection simplex, you know, whatever. But it's non-derivatives. And it'll take some iterations. And you can look at the history as there's a history thing there. And you can see what things are changing in the net present value. And then you can copy that into Excel, make your plot to see the function change for that value. So the same mechanisms, the same things we did in Excel, we're doing here, but instead of using simple little equations in Excel, we're actually launching entire applications on the computer. Okay. It's more or less converging here to about 0.52, $94 million. Okay. So that's basically showing you the kind of things that are needed to be done. You have to be able to access data, numbers. You have to be able to launch different applications in the right order. You have to be able to link together information, output to input from various applications. And then the optimization, you have to have some way to control the optimization. So that's, in short, what this is trying to provide. Now, I'll let Alex tell about a Pipet project for optimization that takes this as a starting point and makes a more complicated, realistic problem and is doing optimization regarding that. So I'll let you just kind of talk through that.
Let's see here. I'll just get that other project open. Well, so this is more or less the same thing, but a bit more complicated. In this project, you have two reservoirs, a lean gas condensate reservoir and a rich gas condensate reservoir, with a bit different initial compositions and a bit different permeability distributions. And the gas from each of these reservoirs are combined and taken into a process facility with three different stage separators there down to standard conditions. The gas from the second stage and out is taken to fuel flare, so you don't get any revenue from that part. And of course, the liquids from all the separators is the condensate. And then you have a dew point controller that's connected to the gas from the first stage separator, and that splits into NGL and gas. And that gas is split into a sales gas fraction and an injection gas fraction. And that injection gas fraction is again split into injection gas for the lean reservoir and the rich reservoir. So you basically have two things you can control there. You can control the total injection fraction, and the split between sales and injection, and how much of that you want to inject to each reservoir. And then of course you have to, now you can't run the reservoir simulator in one go. You have to update it as you go along to update the injection volumes and the injection gas compositions, because those change with time and are dependent on one another between the reservoirs, since you have this connected or combined processing facility. So the Pipet project gets a bit more complicated, but you still have basically the same principles. And it looks like this when it's implemented into Pipet. Here you first have an initial run, and this runs basically both the two reservoir simulators models used for the rich and lean condensate reservoirs, just for an initial step to create a restart file. And it goes through the processing and the economics calculation for, just going here to see, for that first time step. So here you can see that you have basically the two reservoir simulators running in parallel, with lean and rich gas condensate. And then the product from that is kind of the molar rates versus time, and that's fed into the process facilities and the economic calculations. The content in here is basically the same as so in the previous project. It's a bit more complicated, but nothing too special. And this process facilities is actually launching another instance of Pipet, so it's launching a new Pipet project.
The Pipet is launching itself.
Yeah. And if you want to look at that project, it looks like this. So it basically has some file format translations here to get it into the right, the molar rates into the right format for the process simulator. Then those rates are fed into the process simulator and produced into separate products. There you're adding the two reservoir rates together, and then that's fed into the processing, where you end up with this the same products basically as you had before. A bit more complexity here too, but nothing too major in what's changing. And when the processing is done, you have the project economics, and that's basically the same. You end up with, in this case, a net present value per time step. That has to be summed together when all the simulations are finished. And then, since this has to be done in intervals with simulator restarts, you have to do some data aggregation, and you have to add together the results from each restart run of the simulator, and that's done in here. And that's basically what's done for each time step, like here. And then you go up again. So first you do this one-day initial run, and then you have to do a transition run to kind of prepare the models for the restart loop, and that's it's kind of made to make everything on a common time basis and things like that. But it's basically doing the same as here, only doing it now with the restart data sets. And then that's after this is done, then you do basically the same again multiple times in this restart runs. Composite. It just launches the models for a given period of time, and then it adds on to kind of processes everything, and then when all the processing is done, it restarts the reservoir simulators again, and so on. Kind of incrementally increase the time until you reach the end time that you've set. In this case, 15 years. And then when kind of all the simulation is done here, then you add together the net present value to get one single number, since you have it kind of as a net present value versus time after the simulation is done. You end up with simple single net present value number here. This is not the right file. I don't think I have it connected, but yeah, so you end up with one single net present value number in this case. It's basically the same. Now I've connected everything, kind of all the parameters you want to control in this project. It's basically the total injection fraction. That's, if you go back to the process diagram, that's then the split between what's sold as sales gas and what's reinjected in total. That's this number here, it's currently 0. And then you have the lean injection fraction, that's also an important variable. And that's basically the split between the lean and the rich gas condensate for injection. You can either choose to to inject everything to one reservoir or divide it up. And then you have the injection end time, how long you want to inject for. It's the main three variables in this project. And then there's of course a lot of different things that goes into controlling it, like the initial gas price, the initial NGL price, and condensate price, and if you want to have price escalation, you can have that too. And then you have the discount factor. And then when all this is the summation is done, it pulls in the net present value and the cumulative condensate produced and gas produced and NGL produced. Then you can start doing optimizations and see what effects and gains you get from injecting more gas and less gas. So you can try to do that, for instance, with zero injection. Then you get $243 million in net present value. If you try to change that and run it, then you can see the difference. It takes about a minute to run this model now.
So what it's doing, it's actually running the same reservoir simulation model that we showed first, which took a couple of seconds. But it's got two of those. But it's running in restarts of 1 year at a time. I think 1 year.
Well, I've set it to 5 years now, actually,
okay,
to make it a bit faster.
Okay.
That's also controlled by this optimizer. You have the step size, how long you want to run it for each iteration.
So every 5 years it'll update the injection volumes and the injection composition. But you can change that to do it every year, or you can do it every 10 years, whatever you like.
Or every day if you like. Yeah, and then it pulls in a couple of thoughts later. Then you can look at this. The circles here are case without any injection at all, and the red line is the current case. If you look at the gas volumes, then of course you'll have less sales gas the first 10 years, since you're injecting more 10 years to 50% of the gas, but then you don't get this the blowdown period for later, and then you get higher condensate recovery, and you actually get lower cash flow the first years, but you keep it up for much longer. If you want to look at the net present value, it's now 324 million. So you gain, in this case, you gain $70 million by injecting half the gas for 10 years. Then you can, of course, do optimizations on this.
So the idea in this case is that you've got two reservoirs you can inject into. One is leaner, one is richer. You would think intuitively you get more condensate from the richer. But if the richer reservoir has more heterogeneities, then the injected gas is less efficient at sweeping that rich gas. So if the lean gas system reservoir is more homogeneous, then it would actually probably, I don't know, that's why we do the optimization, is where's the gas utilized most effectively? By injecting into reservoir gas, rich gas, or the lean gas? And really this is the mechanism for trying to assess that. And how much gas and for how long. Those are the main things. So, it gives you a feeling. Now, building this takes considerably longer, obviously, than building the initial Excel sheet that I gave you guys, right? But the level of accuracy, the level of the model, and of course this is a much more complicated. You can't, in an Excel sheet, simulate sweep efficiency for a partially miscible gas injection. I mean, it's just, you can't do it with Excel. And so you basically have grown out of the solution world of an Excel problem. You're now in the world of reservoir simulation, processes, and so forth. And the question is, how do I do the same thing we did in our Excel problem? And this is trying to provide a platform to do that. But of course it takes time to learn how to do it and then to actually do it. And a number of you, Sylvia's the most recent victim, Mohammed, and everybody who started learning it, they have the learning curve to get up. Steiner's been using it. There's definitely a learning curve to it, but it provides the mechanism, the facilities, the software, IT capabilities to do integration and optimization outside of an Excel environment using the actual models that you're using today. So that's the goal, that's the hope, that we'll be able to do this kind of thing for large-scale projects. We're doing it in Petrobras, and we're doing it in Ulstad, Haltenmonk, the whole area there. All of the models are being built and run this way. So I think it's promising. We're not on the moon yet, but we're somewhere between the start of the program and getting there. So anyway, that's just an illustration of what's being done. And that's any questions? Yeah.
Is sensor a commercial simulator?
Yes. It's for compositional problems. It's maybe 2 to 10 times faster than Eclipse 300. But
for research, I think it's free for students.
Yeah, it's free for students for research.
Up to 6,000 cells.
Yeah, up to 6,000 cells. Which there's really no limit. There are no, you can make links to as many things as you want. Once the links are created, the links can be used as variables or constraints or anything. There's no limits.
In this project, I have some 40 links, but we can also have considerably more.
Yeah, this links utility is kind of creating an Excel-like database of cells, okay, in one place. Because these numbers it's linking to are spread amongst maybe 5 or 10 or 15 files, different locations in the files. So it kind of puts it to you in a library, in a condensed library.
Solar, so the method that is rolled for the solar, I mean, it depends on the initial value.
Yes.
The art is
yes. Every nonlinear solver has.
Because this solver, I think, that's working on derivative.
No derivatives being used here.
So I'm not sure about it becomes the initial guess.
Yes.
Yeah.
It is.
Yeah, because if you have the surface of the two bowls, like we have, if you start in the bowl A area, you're going to find probably that maximum there. And if you start in the bowl area here, you're going to find this maximum.
Well, I have one that's not dependent on the initial value, and that's the evolutionary strategy.
Now that's
But that's kind of a special case.
there's algorithms that are designed to
But I think this one is runs only, right? But
no. You have to take the book that Bjarne was teaching from, and there's a section about the Nelder-Mead method, and
It has a very consistent set of rules that it follows, but it doesn't take derivatives, it only tests new values, and there's a set of rules how to test those values if they're less than the previous value and higher than the previous value.
And you can take any, like the solver that's in Excel. It's from a company called Frontline, and the Frontline solvers are actually in Python as a plugin, but you have to pay for that because the Frontline solver is you have to pay for it. The one in Excel is free, of course, kind of free. But you can select the Frontline solver, which is derivative based, and use that, but you have to have a license for it. Or you can build your own, you can write your own solver and plug it in. That's what Alex has written, a couple of solvers like that. Okay? Anyway, the idea is that there are mechanisms of doing similar things that we did in the Excel problem, outside of Excel for more complicated systems, and that's Mike. I don't know if you have any final words relative to what we.
No, I think it's go home. We have a couple glass of beer. Those PhD students that course they selected to have it part of the full course. We have on an individual basis to discuss what extra assignment we have to do to get a full credit, so that will build it in a course. For the master students that take that course, part of that course, in fact, will be part of their curriculum, and next week you get exactly an idea what the exam, what is the requirement for that master course. Not everything will be there, but only ingredient from that course will be there. So that's basically all, and what I'll ask you that when you leave the room, please take with you all this stuff.